Dinosaurs. The ancient giants that once ruled the earth. Creatures so vast, so strange, and so powerful that their bones whisper tales from a time before humankind. A time when towering forests stretched endlessly, when strange skies watched over an earth untamed, and when life moved to a rhythm we can only begin to imagine. Tonight, as you close your eyes and drift into a state of quiet rest, let's take a journey, one that stretches back hundreds of millions of years. A journey to an era when our world was unlike anything we know today. Where creatures as large as houses and as fast as modern predators roamed across landscapes lost to time. Dinosaurs were here long before us. Their world was filled with dense jungles, roaring volcanoes, vast deserts, and endless oceans teeming with life. They ruled for over 160 million years, adapting, evolving, and shaping the very planet beneath their feet. Some were as small as chickens, darting through undergrowth, hiding from predators. Others were massive, their footsteps shaking the ground, their shadows stretching far under a primeval sun. But what were dinosaurs, really? Were they slow-moving, cold-blooded monsters? Or were they intelligent, fast, and perhaps even more bird-like than we ever imagined? Scientists have spent centuries trying to answer these questions, piecing together fragments of an ancient puzzle, bones, footprints, and fossils frozen in time. And so, our journey begins. We'll step back into the past, uncovering the story of dinosaurs from their very origins. We'll explore how they came to dominate the world, how they lived, how they hunted, and how they cared for their young. We'll visit the depths of prehistoric oceans, where enormous marine reptiles ruled the waters. We'll soar through the skies with the pterosaurs, watching the world below from heights never before reached by a living creature. But this story isn't just about their rise, it's also about their fall. We'll explore the theories of their extinction, the mysterious event that wiped out nearly all life at the end of the Cretaceous period. Was it an asteroid? Volcanic eruptions? A slow, inevitable change in climate? And perhaps, most intriguingly, we'll uncover the legacy they left behind. Because, in a way, dinosaurs are still here. They walk among us in the form of birds, their closest living relatives. With every flutter of wings, every chirp, every soaring eagle high above, we see glimpses of an ancient past that refuses to be forgotten. So, as you settle in and let your thoughts drift, let the story of the dinosaurs unfold around you. Imagine the dense, misty forests of the Jurassic. The sun-baked plains of the Cretaceous. The deep, roaring oceans of the Mesozoic. This is the story of the dinosaurs. And it all begins, millions of years ago. Our journey begins not in a time of towering giants or terrifying predators, but long before that, at the very dawn of the dinosaurs. To truly understand these creatures, we must travel back over 250 million years, to a time known as the Triassic period. The world then was nothing like the one we know today. There were no lush, green continents teeming with life. Instead, nearly all the land on Earth was connected, forming one massive supercontinent called Pangaea. This was a vast and arid landscape, with sprawling deserts stretching as far as the eye could see. The air was thick and hot, the seasons unpredictable, and the first dinosaurs were only just beginning to take their first steps into history. At this time, dinosaurs were not the dominant creatures of the Earth. They were small, quick-footed, and in many ways, unremarkable compared to the massive reptiles that already roamed the land. The real rulers of the Triassic were creatures known as archosaurs, the ancestors of both dinosaurs and crocodiles. These early reptiles were diverse and powerful, filling every niche of the food chain. Some, like the Postosuchus, were fierce predators, stalking the land with sharp teeth and a powerful bite. Others, like the Placerias, were squat, herbivorous creatures with tusks used for defense. But something was about to change. The end of the Triassic brought with it a great extinction event, one that wiped out much of the life on Earth. No one knows exactly what caused it. Some scientists believe it was a series of enormous volcanic eruptions, filling the skies with toxic gas and choking the land with fire. Others suggest it was a sudden shift in climate, a slow and inevitable transformation that reshaped the balance of life. Whatever the cause, one thing became clear: the dominant creatures of the Triassic were gone, and a new group of animals was about to rise. And so, we enter the Jurassic period, the true golden age of the dinosaurs. Now, the world had changed. Pangaea had begun to break apart, forming new landmasses, new oceans, and new climates. The Earth became warmer, wetter, and more hospitable to life. Vast forests of ferns and towering conifers spread across the land. The air hummed with the sounds of insects, primitive mammals, and, for the first time, the calls of dinosaurs. It was during this time that some of the most famous dinosaurs began to emerge. Towering above the forests were the mighty sauropods, some of the largest creatures to ever walk the earth. The Brachiosaurus, with its long neck reaching high into the trees, feeding on leaves that no other animal could reach. The Diplodocus, a gentle giant stretching over 80 feet in length, moving slowly and deliberately across the plains. But while these herbivorous behemoths wandered the land, there were others lurking in the shadows, ready to strike. The Allosaurus, a fierce predator with powerful jaws and razor-sharp claws, stalked the Jurassic landscape. Unlike the later Tyrannosaurus rex, Allosaurus had long arms and strong claws, which it likely used to grip and slash at its prey. It was an efficient hunter, one of the deadliest of its time. Yet dinosaurs weren't the only creatures to thrive in this ancient world. The skies, once empty, had now begun to fill with life. The first true flying reptiles, the pterosaurs, soared above the land. These weren't dinosaurs, but they were close relatives, sharing the same ancestry. Some, like the pterodactylus, had long, slender wings and sharp beaks, gliding effortlessly over prehistoric coastlines. Others, like the Dimorphodon, had powerful jaws and a short, stocky body, perhaps using their wings to swoop down on unsuspecting prey. As the Jurassic period continued, dinosaurs grew larger, faster, and more specialized. They adapted to every corner of the Earth, from dense jungles to open plains, from towering mountains to coastal shores. But even this golden age would not last forever. And so, we move forward in time once again, to the final act of the dinosaur era, the Cretaceous period. By now, the world had changed dramatically. The continents had drifted further apart, creating new oceans and new climates. The air was filled with the sounds of birds, the distant relatives of dinosaurs, whose wings now beat in the skies above their ancient cousins. Flowers had begun to bloom for the first time, spreading color and scent across the land. It was in this world that some of the most famous dinosaurs of all time lived. The Triceratops, with its massive frilled head and 3 sharp horns, one of the last great herbivores to roam the earth. The Velociraptor, smaller than many imagine, but lightning-fast and intelligent, its sharp claws used not just for hunting, but perhaps even for communication. And then, of course, there was the Tyrannosaurus rex, one of the most iconic predators in history. A creature of immense power, with a bite force greater than any land animal before or since. Though its small arms have often been a source of speculation, its overall size, intelligence, and sheer strength made it one of the most formidable hunters to ever exist. The Cretaceous was a time of abundance, a thriving world of life and diversity. But, as with all things, it had to come to an end. And that end came suddenly. 66 million years ago, something catastrophic happened. A 6-mile-wide asteroid struck the Earth near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact was instantaneous, releasing energy equivalent to billions of atomic bombs. A firestorm of debris shot into the atmosphere, igniting forests, boiling oceans, and shrouding the world in darkness. For years, the skies remained covered in thick clouds of dust and ash, blocking out the sun. Temperatures plummeted, plant life withered, and the great dinosaurs, the rulers of the earth for over 160 million years, could not survive. And so, their reign came to an end. But in the shadows, in the cracks and crevices of the earth, small creatures scurried. Tiny mammals, barely noticed during the time of the dinosaurs, now found themselves in a new world. And from them, a new chapter of life would begin. But the story of the dinosaurs does not end here. Because in many ways, they never truly disappeared. For their closest relatives still roam the earth today. The birds that sing in the trees. The eagles that soar above the mountains. The tiny sparrow on your windowsill. Each of them carries the legacy of the great reptiles that once ruled the world. And so, as we close this chapter of our journey, we remember, dinosaurs are not just creatures of the past. Their story continues, even now. As we continue our journey through the age of dinosaurs, let's take a closer look at some of the incredible creatures that once roamed the earth. These were not simply giant lizards, they were diverse, intelligent, and perfectly adapted to their environments. Each species had its own way of surviving, its own role in the vast and complex ecosystems of the Mesozoic era. Let's begin with the Jurassic period, a time when some of the most famous dinosaurs began to flourish. Picture, for a moment, a vast floodplain stretching as far as the eye can see. The air is thick and humid, the sky a deep shade of blue, with occasional wisps of white clouds drifting overhead. Towering conifer trees stand like ancient sentinels, their branches swaying gently in the warm breeze. Beneath them, enormous creatures move slowly and deliberately, their massive bodies shaking the ground with each step. This is the world of the Brachiosaurus, one of the largest land animals to have ever lived. Unlike many other giant dinosaurs, Brachiosaurus carried itself differently. It stood taller at the front, its long, giraffe-like neck reaching high into the canopy to feed on leaves no other herbivore could reach. Imagine the soft rustling of leaves as it stretches its long neck upward, pulling branches into its powerful jaws and stripping them clean with peg-like teeth. But despite its size, Brachiosaurus was not invincible. In the dense jungles nearby, another creature lurked, a predator built for speed and strength. The Allosaurus, one of the most fearsome carnivores of the Jurassic, was a relentless hunter. Unlike the later Tyrannosaurus rex, Allosaurus had longer arms with sharp claws, which it likely used to grasp and tear into its prey. Fossil evidence even suggests that Allosaurus may have been a pack hunter, working together to take down prey much larger than itself. Imagine a scene in the fading light of dusk. A small herd of Stegosaurus, their backs lined with large, bony plates, move cautiously through a clearing. Their tails, tipped with sharp spikes known as the thagomizer, sway back and forth, a warning to any predator that might dare attack. Suddenly, an Allosaurus emerges from the shadows, its yellow eyes locked onto a lone Stegosaurus at the edge of the group. It lunges, but the Stegosaurus swings its powerful tail with astonishing speed, striking its attacker with a force capable of breaking bone. The predator stumbles back, wounded, as the herd moves deeper into the forest, disappearing into the safety of the trees. But the Jurassic was not just a time of giants on land. The skies were filled with creatures unlike anything we see today. Pterosaurs, the first true flying vertebrates, soared above the ancient landscapes. These weren't dinosaurs, but they were closely related, sharing a common ancestor. Some, like Rhamphorhynchus, had long, slender wings and a tail tipped with a diamond-shaped flap of skin, perhaps used for steering. Others, like Pterodactylus, had shorter tails and a more streamlined body, perfect for gliding over prehistoric coastlines. But the true kings of the Mesozoic skies wouldn't appear until the Cretaceous period, when giants like Quetzalcoatlus, a pterosaur with a wingspan of over 30 feet, would rule the air. And so, time marches forward. The Jurassic world, with its towering forests and lumbering sauropods, slowly gives way to a new era, the Cretaceous period. By now, the continents have drifted even further apart. Vast inland seas cover much of the land, creating new environments where dinosaurs continue to evolve and thrive. Some species become smaller and more agile, while others grow into true titans. One of the most fascinating changes in the Cretaceous was the rise of new, more specialized predators. While the Jurassic had Allosaurus, the Cretaceous had something far deadlier, Tyrannosaurus rex. Tyrannosaurus was unlike any predator before it. With a skull over 5 feet long, powerful jaw muscles, and teeth the size of bananas, it had one of the strongest bite forces of any land animal in history. But what made it truly remarkable was its intelligence. Studies of its fossilized brain case suggest that T-Rex had excellent vision, a strong sense of smell, and problem-solving abilities that made it a highly efficient hunter. But not all dinosaurs in the Cretaceous were monstrous killers. Some were incredibly small, agile, and even feathered. Take the Velociraptor, for example, not the oversized Hollywood version, but the real Velociraptor, which was about the size of a turkey. Fossil evidence suggests that it was covered in feathers, and its famous sickle-shaped toe claw may have been used not only for hunting but also for climbing and gripping prey. And then there were the herbivores, which had evolved new and fascinating ways to defend themselves. The Triceratops, with its massive frill and 3 sharp horns, could stand its ground against even the most fearsome predators. The Ankylosaurus, covered in thick, bony armor and wielding a powerful tail club, was like a walking tank, capable of delivering bone-crushing blows to any attacker. One of the strangest creatures of the Cretaceous was Therizinosaurus, a towering, feathered dinosaur with long, side-like claws. For years, paleontologists weren't sure what to make of it. At first, they thought it might be a predator, using its claws to tear into flesh. But later evidence showed that it was likely a herbivore, using its enormous claws to pull down branches and strip them of leaves. The Cretaceous period was truly a time of incredible diversity. But even as dinosaurs reached their peak, their time was running out. As we near the end of our journey, we will explore the dramatic final days of the dinosaurs, the moment when an asteroid changed the course of history forever. But for now, imagine the world as it was in its prime. A landscape teeming with life, where every shadow holds a predator, every tree shelters prey, and every gust of wind carries the distant calls of creatures that no longer walk the earth. Though they are gone, their story continues to be uncovered, piece by piece, fossil by fossil. And with each discovery, we come closer to understanding the incredible world of the dinosaurs, one that existed long before us, and in many ways, still lingers in the life that surrounds us today. Dinosaurs weren't just rulers of the land, they were part of an intricate web of life that extended into the skies, the waters, and deep into the ecosystems that shaped their world. Their behaviors, their adaptations, and even their interactions with one another paint a picture of creatures far more complex than simple, lumbering beasts. For many years, dinosaurs were thought to be slow, dull-witted creatures, reptilian brutes driven only by instinct. But as scientists have uncovered more about their brains, behaviors, and their close relatives, the modern birds, it has become clear that some dinosaurs may have been far more intelligent than we once believed. Take the Troodon, for example. This small, bird-like dinosaur had one of the largest brain-to-body ratios of any known dinosaur, suggesting high intelligence. Troodon had keen eyesight, excellent depth perception, and a powerful sense of smell, making it a highly skilled hunter. Some paleontologists even believe it may have had the ability to solve problems, work in packs, and possibly even communicate through vocalizations. Could it have had a social structure? Could it have used strategy when hunting? While we may never know for sure, fossil evidence of similar species suggests that at least some dinosaurs may have lived in family groups, cared for their young, and even worked together for survival. Another intriguing case is Deinonychus, a relative of Velociraptor. Studies of fossilized trackways suggest that these dinosaurs may have coordinated their movements when hunting, much like modern-day wolves. If true, this means that at least some raptors were capable of complex social behavior rather than simply acting on individual instinct. But intelligence is only part of the picture. Another question scientists have pondered is, what did dinosaurs sound like? Hollywood often portrays dinosaurs with deep, bellowing roars and high-pitched screeches, but the reality may have been quite different. Since many dinosaurs are closely related to birds, it's likely that some of them may have produced sounds similar to those of modern-day cranes, cassowaries, or even ostriches. Some scientists believe that larger dinosaurs, like hadrosaurs, may have used their hollow crests as resonating chambers to produce deep, bellowing calls that could travel for miles. These calls could have been used for communication, warning others of danger, calling for mates, or even establishing dominance within a herd. Meanwhile, smaller dinosaurs may have produced sounds through hissing, growling, or primitive forms of vocalization. Fossilized throat structures in some species suggest the possibility of complex sounds, though exactly what they would have sounded like remains a mystery. One of the most remarkable discoveries in paleontology is evidence that some dinosaurs were highly devoted parents. For many years, dinosaurs were assumed to be like modern reptiles, laying their eggs and abandoning them. But discoveries of nesting sites, fossilized embryos, and preserved nests tell a different story. The Maiasaura, whose name means good mother lizard, is one of the best examples of parental care in dinosaurs. Fossilized nests containing eggs, hatchlings, and juveniles suggest that Maiasaura mothers did not simply leave their young to fend for themselves. Instead, they returned to their nests to provide food, much like modern birds do. Other dinosaurs, such as Oviraptor, were once thought to be egg thieves, hence their name, which means egg thief. But later discoveries revealed that these dinosaurs were actually protecting their own nests. Fossils of Oviraptor have been found in a brooding position, sitting atop their eggs just as birds do today. Some dinosaurs may have even built complex nesting colonies, returning to the same sites year after year to lay their eggs in carefully arranged patterns. This suggests that social structures among dinosaurs may have been more advanced than we previously thought. For a long time, the appearance of dinosaurs was left entirely to imagination. Were they dull, gray and brown creatures, blending into their environments like modern reptiles? Or were they vibrant and colorful, covered in striking patterns and iridescent hues? Thanks to advancements in fossil analysis, we now have evidence that at least some dinosaurs had feathers, and with those feathers, possibly bright colors. Fossilized melanosomes, tiny structures in feathers that determine pigmentation, have been found in certain dinosaur fossils, allowing scientists to reconstruct their likely colors. The Anchiornis, for example, was a small, feathered dinosaur with a striking black and white body and patches of bright red on its head, similar to a woodpecker. Others, like Microraptor, may have had shimmering, iridescent feathers, much like modern crows or ravens. But what about the giant dinosaurs? The ones too large to have feathers? While some, like T-Rex, may have had a covering of downy fuzz as juveniles, most larger species likely retain scales. Still, that doesn't mean they were dull. Many modern reptiles, like lizards and snakes, have vibrant patterns and colors, so it's possible that some dinosaurs had striking visual displays to attract mates, intimidate rivals, or blend into their surroundings. Though dinosaurs ruled the land, the oceans were home to an entirely different group of ancient reptiles. These were not dinosaurs, but marine reptiles, creatures that had evolved to dominate the vast prehistoric seas. One of the most terrifying was Mosasaurus, a massive, crocodile-like predator that patrolled the waters of the late Cretaceous. Growing up to 50 feet long, it had a double-hinged jaw that allowed it to swallow prey whole, much like modern snakes. Then there were the pliosaurs, short-necked marine reptiles with enormous skulls and powerful flippers. One of the most famous was SleepyFacts, a Jurassic-era predator with a bite force that could rival even T-Rex. But not all marine reptiles were massive predators. The ichthyosaurs, for example, were streamlined, dolphin-like creatures that filled the same ecological niche as modern whales. They were fast, agile, and likely gave birth to live young, rather than laying eggs on land. As we uncover more about these ancient creatures, we begin to see a world that was teeming with life, intelligence, and complexity. Dinosaurs weren't just prehistoric monsters, they were adaptable, evolving animals, shaped by their environments in ways we are only just beginning to understand. In the next section, we will step into the final days of the dinosaurs, witnessing the moment when everything changed. But before we do, let's take one last moment to imagine their world, a place of towering trees, thundering footsteps, and skies filled with creatures that once ruled the world. There is one name that stands above all others. One creature that has captivated imaginations for over a century, earning its place as the undisputed king of prehistoric predators. A name that strikes fear even millions of years after its extinction, Tyrannosaurus rex. Towering over its domain at nearly 40 feet long and weighing up to 9 tons, T-Rex was the apex predator of the late Cretaceous period, a time when dinosaurs were at their most evolved and diverse. This was not just another carnivore, it was a finely tuned killing machine, one of the most powerful terrestrial predators to have ever walked the earth. Its massive skull alone was nearly 5 feet long, packed with 60 serrated, banana-sized teeth that could crush bone with a single bite. Unlike the sharp, knife-like teeth of raptors or other theropods, T-Rex's teeth were designed for pulverizing rather than slicing. When it bit down, its teeth didn't just puncture flesh, they shattered bones, delivering a crushing force estimated at over 12,000 pounds per square inch, stronger than that of any known land animal. In comparison, a modern great white shark has a bite force of about 4,000 psi, and a lion's is only about 1,000 psi. T-Rex didn't just kill its prey, it obliterated it. Its skull was reinforced with thick, interlocking bones, acting like a biological shock absorber. This allowed it to withstand the immense stress of its own bite force, something no other predator of its size could match. Prey that fell victim to T-Rex had no chance. If it managed to clamp its jaws around a struggling dinosaur, it wouldn't simply hold on. It would crush through muscle, organs, and bone in a devastating, single motion. But T-Rex was more than just a walking set of jaws. Its keen senses made it a near-perfect hunter. For decades, it was assumed that T-Rex had poor vision, an outdated belief that stemmed from early comparisons to modern reptiles. However, new studies show that its forward-facing eyes gave it exceptional depth perception, much like an eagle or an owl. In fact, T-Rex had some of the largest eye sockets of any land predator, granting it vision that was up to 13 times sharper than a human's. It could likely spot movement from miles away, tracking prey with terrifying accuracy. And then there was its sense of smell. The olfactory bulbs, the part of the brain responsible for processing scent, were unusually large in T-Rex, meaning it had an exceptional ability to detect odors over long distances. Some scientists believe its nose was as powerful as that of modern vultures, capable of sniffing out carcasses from miles away. This suggests that, in addition to being a lethal hunter, T-Rex was also a skilled scavenger, taking advantage of already weakened or dead prey. If another predator made a kill, T-Rex may have used its sheer size and power to steal food, much like modern lions do from smaller carnivores. Despite its bulk, T-Rex wasn't necessarily slow. Early portrayals often depicted it as a sluggish, plodding monster, but evidence now suggests otherwise. Its long, muscular legs were built for efficient movement, allowing it to cover vast distances without tiring. While it likely couldn't sustain high speeds for long, some estimates suggest that it could reach speeds of up to 25 miles per hour, faster than an Olympic sprinter. A human on foot wouldn't stand a chance. The debate over whether T-Rex was a pure hunter or an opportunistic scavenger has raged for years, but the truth is likely somewhere in between. Like modern apex predators, it likely took advantage of whatever opportunity it had, whether that meant ambushing prey, chasing down weaker dinosaurs, or feasting on a decaying carcass. With its immense power, it didn't need to be picky. Even the much-mocked tiny arms of T-Rex were likely more useful than they appear. Though comically short in proportion to its body, each arm was still about 3 feet long, with thick bones and powerful muscles. Studies suggest that they may have been used for gripping struggling prey, helping the dinosaur push itself up from a resting position, or even for mating purposes. While not its primary weapon, these small but muscular limbs weren't completely useless. Fossil evidence shows that T-Rex was also a survivor. Some specimens have been found with healed wounds, including bite marks from other T-Rex individuals. This suggests that these predators may have fought one another, either over food, territory, or mates. Battles between two T-Rex would have been earth-shaking events, massive predators clashing in displays of raw power. Its reign as the top predator lasted nearly 2 million years, an impressive stretch of dominance in evolutionary terms. But even the mighty T-Rex couldn't escape fate. When the asteroid struck Earth 66 million years ago, it triggered a series of catastrophic events that wiped out nearly 75% of all life, including all non-avian dinosaurs. The skies darkened, temperatures dropped, food sources disappeared. T-Rex, once the king of its world, found itself in a realm it could no longer rule. And yet, it lives on. Not just in museums, or movies, or childhood imaginations, but in a very real, biological sense. Modern birds are its descendants, carrying fragments of its DNA into the present day. The next time you see a hawk soaring overhead, or hear the shriek of a crow, remember, you're listening to the echoes of T-Rex. Its reign may have ended, but its legacy remains eternal. The largest creatures to ever roam the earth were dinosaurs, but when it comes to the largest prehistoric reptile beneath the waves, we must turn to an entirely different branch of ancient giants. While dinosaurs ruled the land, the oceans were dominated by marine reptiles, powerful creatures that evolved to master life in the water. And among them, one of the most formidable and massive was Mosasaurus, an apex predator that reigned supreme during the late Cretaceous period. Mosasaurus was a true sea monster, growing up to 50 to 60 feet, 15 to 18 meters, long, rivaling the size of a modern humpback whale. Unlike earlier marine reptiles such as the long-necked plesiosaurs or dolphin-like ichthyosaurs, Mosasaurus had a streamlined, elongated body, perfectly designed for powerful, high-speed swimming. It was neither slow nor clumsy. It was a fast-moving, ambush predator that used explosive bursts of speed to overtake its prey. One of its most distinctive features was its massive skull, which could reach up to nearly 6 feet, 1.8 meters, in length. Its jaw was packed with over 40 sharp, conical teeth, perfectly designed to grip slippery prey like fish, sharks, and even other marine reptiles. But Mosasaurus didn't just bite. It had a double-hinged jaw and flexible skull, similar to modern snakes, allowing it to open its mouth exceptionally wide. This meant it could swallow prey whole, rather than having to tear it apart. Even more terrifying was the presence of a second set of teeth in its throat, known as pterygoid teeth. These backward-facing teeth helped to secure prey, ensuring that once something was in its mouth, there was no escape. Modern snakes use a similar mechanism when swallowing their food. Once Mosasaurus clamped down, there was no chance of wriggling free. Mosasaurus wasn't just a brute force predator, it was also highly evolved for ocean life. Unlike earlier marine reptiles that had to return to land to lay eggs, Mosasaurus was fully aquatic, giving birth to live young in the water. This adaptation allowed it to dominate the open seas, never needing to leave the safety of its deep-water kingdom. Its limbs had transformed into powerful flippers, and unlike early marine reptiles that relied mostly on their tails for propulsion, Mosasaurus used both its long, muscular tail and paddle-like limbs to navigate the ocean. This combination gave it remarkable agility for an animal of its size, allowing it to chase down prey or ambush it from below. The shape of its tail fin is one of the more recent discoveries in paleontology. For many years, scientists believed Mosasaurus had a simple, lizard-like tail. But fossil evidence now suggests that it had a crescent-shaped, shark-like tail, making it an even more efficient swimmer. This streamlined body plan meant that Mosasaurus was not just a predator, it was an apex predator, rivaling even the largest sharks of its time. Speaking of sharks, Mosasaurus lived alongside some of the most dangerous marine animals ever to exist, including Cretoxorina, an enormous shark sometimes called the Jinsu shark, which grew over 25 feet long and had a bite comparable to that of a great white. But despite the presence of such competition, Mosasaurus sat at the very top of the food chain. Fossil evidence shows that it even preyed upon other large marine reptiles, including other mosasaurs. This suggests that Mosasaurus wasn't just a hunter of fish or squid, it was an opportunistic predator that would eat anything it could overpower, even its own kind. Some scientists believe that Mosasaurus may have hunted like modern killer whales, using intelligence and strategy to work together in groups to take down large prey. While we have no direct evidence of pack behavior, its dominance in the ecosystem and the sheer scale of its existence suggest that it was an animal that didn't just rely on brute force, it likely had finely honed instincts that allowed it to outmaneuver prey and competitors alike. Despite its dominance, Mosasaurus, like all large marine reptiles, met its end during the mass extinction event 66 million years ago. When the asteroid struck, it didn't just wipe out the land-dwelling dinosaurs, it sent shockwaves through the oceans. Dust and debris filled the atmosphere, blocking out sunlight and collapsing the marine food chain. As plankton and smaller marine creatures died out, the larger predators that relied on them quickly followed. The mighty Mosasaurus, which had ruled the seas for millions of years, vanished along with the dinosaurs on land. But its legacy remains. Today, its closest living relatives are monitor lizards and snakes, creatures that still carry echoes of their prehistoric ancestor. And in the fossilized remains scattered across ancient seabeds, we can still glimpse the monstrous form of the last great marine predator of the dinosaur age, one of the most terrifying rulers of the prehistoric seas. Among all the giants that ever walked the earth, one species stood above the rest in sheer size and mass, Argentinosaurus, the undisputed titan of the land. This colossal herbivore lived during the late Cretaceous period, around 95 to 100 million years ago, in what is now Argentina. It belonged to a group of dinosaurs known as titanosaurs, a branch of long-necked sauropods that included some of the largest creatures to have ever existed. Argentinosaurus was truly massive. While no complete skeleton has ever been found, fossil evidence suggests that it reached lengths of 100 to 115 feet, 30 to 35 meters, and weighed between 90 and 110 tons. To put that into perspective, it was as long as a blue whale and as heavy as 15 elephants combined. Its sheer size meant that it had no natural predators once it reached adulthood. Few, if any, carnivores would dare to challenge such an enormous animal. Like other sauropods, Argentinosaurus had a small head compared to its gigantic body, with a long, slender neck that allowed it to reach vegetation high above the ground. Its neck alone was estimated to be over 30 feet, 9 meters, long, making it possible for the animal to feed on treetops that other herbivores couldn't reach. Unlike earlier sauropods, titanosaurs like Argentinosaurus had wider, more robust bodies, with strong, column-like legs built to support their immense weight. Its feet were specially adapted for carrying such a heavy load. Each foot had a soft, padded structure, much like modern elephants, to help absorb the shock of its massive frame as it moved. This padding acted as a cushion, preventing stress injuries that could have been fatal for such a large animal. Its tail was equally impressive, extending nearly the same length as its neck, and may have been used for defense or balance. Despite its enormous size, Argentinosaurus was likely constantly on the move, requiring massive amounts of food to sustain itself. Paleontologists estimate that it may have eaten hundreds of kilograms of plants per day, stripping trees bare as it roamed in search of more vegetation. Its long digestive system allowed it to extract as much energy as possible from the tough, fibrous plants it consumed, a necessary adaptation for an animal of its size. One of the biggest mysteries surrounding Argentinosaurus is how it moved. Due to its sheer size, it likely had a slow but steady gait, with an estimated walking speed of only 5 miles per hour, 8 kilometers per hour. However, recent biomechanical studies suggest that its powerful legs and wide stance may have allowed it to move more efficiently than previously thought, possibly covering vast distances in search of food. Given its size, it's unlikely that Argentinosaurus could run. Any attempt to do so would have put enormous strain on its bones and muscles. Argentinosaurus likely traveled in herds, a common behavior among large herbivores. Moving in groups would have offered protection from predators, particularly juvenile individuals that were still vulnerable to attacks from large theropods. Among the primary threats were Giganotosaurus, a massive carnivore that lived in the same region and was one of the few predators large enough to pose a risk to young or weak titanosaurs. Fossil evidence suggests that these predators may have hunted in packs, increasing their chances of bringing down even the largest prey. Reproduction for an animal of this size must have been a slow process. Like other sauropods, Argentinosaurus likely laid eggs, but instead of carefully tending to them, it may have followed a strategy seen in some modern reptiles, burying them in the ground and leaving them to hatch on their own. This method meant that hatchlings were on their own from birth, relying on instinct and rapid growth to survive in a world filled with predators. Juveniles would have been much smaller than adults and likely grew several tons per year to reach their massive size as quickly as possible. Despite being one of the largest land animals of all time, Argentinosaurus and its titanosaur relatives were not invincible. Their enormous size required a delicate balance of food, climate, and resources to sustain them. By the end of the Cretaceous period, changing environmental conditions, shifting ecosystems, and possibly competition from other herbivores may have put stress on their populations. And then, 66 million years ago, disaster struck. The asteroid impact that marked the end of the Cretaceous sent the world into chaos. Massive wildfires, dust clouds blocking out the sun, and a collapse of plant life all contributed to a rapid extinction event. For creatures like Argentinosaurus, which depended on vast amounts of vegetation, the loss of food sources would have been catastrophic. Within a short period, the largest land animal ever to exist vanished from the earth. But Argentinosaurus left behind a lasting legacy. Its fossils remind us of a time when true giants walked the earth, dominating the landscape in a way no modern animal can. Even today, scientists are still uncovering new evidence about its life, movement, and behavior, piecing together the story of the greatest land-dwelling titan the world has ever known. Throughout the reign of the dinosaurs, countless battles played out between predator and prey. Some of these encounters have become the stuff of legend, with fossil evidence revealing the brutal struggles that took place millions of years ago. Among these clashes, a few stand out as the most famous rivalries in prehistoric history, battles between some of the most fearsome predators and the most resilient herbivores ever to walk the earth. One of the most iconic rivalries was between Tyrannosaurus rex and Triceratops, a deadly contest of brute force versus armored resilience. These two titans lived in North America during the late Cretaceous period, around 68 to 66 million years ago, and fossil evidence suggests they clashed frequently. T-Rex, one of the most famous predators in history, was the ultimate carnivore, a massive, bipedal theropod standing 12 feet, 3.6 meters, tall at the hips and measuring over 40 feet, 12 meters, long. Its jaw strength was unparalleled, capable of exerting a bite force of up to 12,800 pounds per square inch, psi, more than any living animal today. With teeth shaped like serrated knives, each measuring nearly 12 inches, 30 centimeters, long, it could crush bone with ease, meaning that even the thickest armor was no guarantee of survival. But Triceratops was no easy prey. As one of the most heavily armored herbivores of all time, it was built like a living tank, measuring 30 feet, 9 meters, long and weighing up to 12 tons. Its huge frill and three sharp horns, which could be over 3 feet, 1 meter, long, provided both protection and a formidable offense. Unlike many other plant eaters, Triceratops could actively fight back, lowering its head and using its powerful neck muscles to drive its horns into an attacker. Evidence of these battles comes from fossilized Triceratops skulls, many of which bear deep bite marks from T-Rex teeth, some of them partially healed, suggesting that some Triceratops survived these encounters. In some cases, the punctures go straight through the frill, showing the sheer force with which T-Rex could attack. However, there are also fossils of T-Rex bones with wounds that match the shape of Triceratops' horns, indicating that sometimes, the hunter became the hunted. Another famous rivalry took place far earlier in the Jurassic period, Allosaurus versus Stegosaurus. These two dinosaurs lived in what is now North America, around 155 to 150 million years ago, and their interactions must have been just as dramatic as those of their Cretaceous counterparts. Allosaurus was the dominant predator of the late Jurassic, growing up to 35 feet, 10.5 meters, long and weighing around 2 tons. Unlike the heavier, bulkier T-Rex, Allosaurus was faster and more agile, with sharp, curved claws and a powerful bite. It had a unique jaw structure that may have allowed it to open its mouth extremely wide, enabling it to strike with devastating bites. Its main prey, however, was the heavily armored Stegosaurus, a plant eater measuring up to 30 feet, 9 meters, long and weighing around 7 tons. Stegosaurus is best known for its distinctive plates running along its back, but its true weapon was its formidable tail, tipped with 4 massive spikes, a structure called the thagomizer. Fossils provide direct evidence of this prehistoric rivalry. One Allosaurus fossil has a deep puncture wound in its pelvis that perfectly matches the shape of a Stegosaurus tail spike. The force required to inflict such a wound suggests that Stegosaurus could swing its tail with enough power to break bone, a deadly counterattack against any predator that got too close. But perhaps one of the most intense rivalries was between Spinosaurus and Carcharodontosaurus, two of the largest carnivores ever to walk the earth. These predators lived in North Africa during the mid-Cretaceous period, around 95 million years ago, and though they occupied different ecological niches, there is evidence that their territories may have overlapped. Spinosaurus, the largest of all known theropods, was a true river monster, growing up to 50 to 60 feet, 15 to 18 meters, long and weighing up to 20 tons. Unlike most large theropods, it had an elongated snout filled with conical, crocodile-like teeth, suggesting it was primarily a fish-eater. Its massive sail, made up of tall vertebrae, remains a mystery. Some scientists believe it may have been used for thermoregulation, while others suggest it was a display feature for intimidation or courtship. Carcharodontosaurus, on the other hand, was a terrestrial predator, similar in size to T-Rex but with a longer, narrower skull and serrated teeth designed for slicing through flesh. It measured around 40 feet, 12 meters, long and weighed up to 8 tons, making it one of the most fearsome land predators of its time. While Spinosaurus likely spent much of its life hunting aquatic prey, its need for vast amounts of food would have inevitably brought it into conflict with Carcharodontosaurus, which hunted large dinosaurs on land. Fossil evidence suggests that these two titans may have clashed over territory or food sources. Some Spinosaurus fossils show signs of teeth marks from large theropods, while some Carcharodontosaurus fossils show damage that could have come from a Spinosaurus bite. Unlike the battles between T. rex and Triceratops, these two predators weren't necessarily hunting each other, but competition over resources could have led to deadly encounters. If a Spinosaurus found itself too far from the water, it may have been vulnerable to a land-based predator like Carcharodontosaurus. Conversely, if a Carcharodontosaurus got too close to the rivers and swamps, it may have found itself in a fight against a semi-aquatic giant that could use its powerful arms and massive jaws to defend itself. Each of these prehistoric rivalries showcases the brutal reality of life during the age of dinosaurs. Whether through epic clashes of strength, tactical ambushes, or territorial disputes, the struggle between predator and prey shaped the evolutionary arms race that led to the dominance of these incredible creatures. The fossil record allows us to glimpse these battles, frozen in time, silent reminders of a world where only the strongest survived. The Earth during the age of dinosaurs was vastly different from the world we know today, a time of extreme climates, shifting landscapes, and frequent natural disasters. From volcanic eruptions to dramatic climate changes, the planet was a volatile, dynamic environment, and it was this ever-changing backdrop that shaped the evolution and survival of the dinosaurs. The Mesozoic era, which spanned from about 252 to 66 million years ago, was divided into 3 periods: the Triassic, Jurassic, and Cretaceous. Each of these periods was marked by unique geological, climatic, and atmospheric conditions that had a profound effect on life during the time of the dinosaurs. Volcanoes, in particular, played a pivotal role in shaping the landscape and the ecosystems in which dinosaurs lived. During the Triassic period, 252 to 201 million years ago, the supercontinent Pangaea was still intact, which meant that vast, uninterrupted landmasses stretched across the planet. The atmosphere was different from today, with higher levels of carbon dioxide, creating a warmer climate overall. The central regions of Pangaea were dry and arid, with vast deserts stretching across what is now North America, Africa, and Europe. Water sources were few, and much of the landscape was barren, supporting only sparse vegetation. In contrast, the coastal regions, where volcanism was especially active, were rich in plant life, which provided sustenance for the early herbivorous dinosaurs. Volcanic activity during the Triassic was frequent and widespread, particularly in the areas where the tectonic plates were slowly starting to pull apart, creating rifts and deep fractures in the Earth's crust. The eruptions of massive volcanoes released enormous amounts of ash and gases, including sulfur dioxide and carbon dioxide, into the atmosphere. These eruptions had a significant impact on the climate, leading to localized temperature fluctuations and contributing to periods of extreme heat followed by cooler intervals. Such environmental stress may have contributed to the end Triassic extinction event, which wiped out many species, paving the way for the rise of the dinosaurs. As the Mesozoic progressed, the world continued to evolve. By the Jurassic period, 201 to 145 million years ago, the supercontinent of Pangaea began to break apart. This division created 2 major landmasses, Laurasia in the north and Gondwana in the south. As the continents drifted further apart, ocean basins began to open, creating new coastlines and shallow seas. These seas were warm, shallow, and teeming with life, ideal conditions for marine reptiles like ichthyosaurs and plesiosaurs to thrive. The climate during the Jurassic was much warmer than today, with high humidity, abundant rainfall, and a lush, green landscape. Dense forests of conifers, cycads, and ferns flourished, providing abundant food for herbivores like sauropods and stegosaurus. Volcanic activity continued during the Jurassic, with eruptions occurring along the rifts where the continents were separating. This created regions of active volcanism, such as those found along the Pacific Ring of Fire. The volcanic islands formed by this activity were home to unique ecosystems, where the flora and fauna adapted to the harsh, volcanic landscapes. These islands provided fertile soil, enriched by ash and mineral deposits from eruptions. However, they also posed a threat to life, as frequent eruptions could destroy entire ecosystems, forcing species to adapt rapidly or face extinction. The Cretaceous period, 145 to 66 million years ago, the final chapter of the Mesozoic, was marked by the peak of dinosaur diversity and the greatest geological changes of the era. The continents continued to drift, with North America, Europe, and Asia separated from South America and Africa. This period saw the opening of new oceanic gateways and the formation of vast inland seas that divided the landmasses. Warm, shallow seas covered much of the Earth, creating rich environments for marine life, including mosasaurs and pliosaurs. The climate remained warm, with high sea levels and lush vegetation that provided abundant food for the herbivores. However, volcanic activity during the Cretaceous was particularly intense, especially in the regions surrounding the Tethys Sea and the Pacific Ring of Fire. The constant tectonic movement beneath the Earth's crust caused large-scale volcanic eruptions, which released vast amounts of ash, sulfur, and carbon dioxide into the atmosphere. These volcanic eruptions played a role in creating the greenhouse effect, which raised global temperatures and contributed to periods of high volcanic activity, with consequences for both terrestrial and marine ecosystems. The impact of these volcanic eruptions on the environment was profound. The release of greenhouse gases led to global warming, while the ash and sulfur particles likely caused temporary cooling and acid rain in some regions. In areas close to the volcanic hotspots, landscapes would have been blanketed in ash, disrupting plant life and making it difficult for herbivores to find food. For carnivores, such changes would have made hunting more difficult, as the available prey would be in short supply. By the end of the Cretaceous, the world was a very different place. The final volcanic eruptions coincided with the asteroid impact that contributed to the mass extinction event that wiped out the dinosaurs. However, the volcanic activity of the Mesozoic also created the landscapes and ecosystems that dinosaurs called home, and it was the interaction of these natural forces, volcanism, shifting continents, and changing climates, that ultimately shaped the fate of these magnificent creatures. In addition to volcanic activity, other natural phenomena played a role in the living conditions of the dinosaurs. Earthquakes and landslides were common, as tectonic plates shifted and collided. These geological disturbances created mountain ranges, valleys, and rivers, which provided diverse habitats for a wide range of species. Coastal regions, with their temperate climates, supported lush vegetation, while interior regions were often drier, with more arid conditions. The conditions of the Mesozoic era fostered not only the evolution of the dinosaurs but also the development of an entire ecosystem, including plants, insects, and other creatures, that would come to define the Age of Giants. The landscape, ever-changing through volcanic eruptions, earthquakes, and continental drift, was a world of constant adaptation and survival, a harsh but beautiful environment that would shape the creatures of the Mesozoic for millions of years. While the massive and well-known dinosaurs such as Tyrannosaurus rex and Triceratops often dominate the spotlight, the Mesozoic world was also home to many lesser-known species that were equally fascinating and played critical roles in their ecosystems. These dinosaurs, while not as famous, provide unique insights into the diversity and complexity of life during the Triassic, Jurassic, and Cretaceous periods. Let's delve into some of these lesser-known dinosaurs, each with its own remarkable features and adaptations. One of the most intriguing, lesser-known dinosaurs from the Triassic period is Herrerasaurus, a small, carnivorous theropod that lived around 230 million years ago in what is now South America. Though not as famous as later predators like T. rex, Herrerasaurus was one of the earliest theropods, providing crucial insight into the early evolution of dinosaurs. It was relatively small, measuring around 10 feet, 3 meters, in length, but it had some characteristics that set it apart from its contemporaries. Herosaurus was a bipedal carnivore with long legs, a slender body, and a sharp, serrated set of teeth that suggest it was a swift and capable predator. However, its most notable feature was its clawed hands, which were unusually large for a dinosaur of its size. These hands likely allowed it to grasp and hold onto prey while delivering a fatal bite, a method of hunting that is similar to that of modern-day birds of prey. Fossil evidence of Herosaurus shows that it inhabited a range of environments, from forests to more open plains, and it may have preyed on smaller vertebrates and early herbivorous dinosaurs. Despite its significance in the early evolution of theropods, it remains a lesser-known dinosaur because of the relatively few fossils that have been discovered. Another lesser-known dinosaur that roamed during the Jurassic period was Brachiosaurus, a giant sauropod that often gets overshadowed by its more famous cousins, like Apatosaurus and Diplodocus. Brachiosaurus was a massive, herbivorous dinosaur that reached lengths of 80 feet, 24 meters, and weighed up to 80 tons. Unlike other large sauropods, Brachiosaurus had a unique body structure. Its front legs were longer than its hind legs, which gave it an upward tilted body and allowed it to reach and feed on vegetation high up in the trees. This adaptation set it apart from other sauropods, which typically fed from the ground. Brachiosaurus lived in lush, forested environments during the late Jurassic, where its long neck allowed it to browse the treetops for leaves, fruits, and other plant material. Its specialized diet helped it to thrive in an environment where other herbivores might have struggled. While not as well known as some other dinosaurs, Brachiosaurus played an essential role in shaping the ecosystems of the Jurassic period by feeding on plant life high above the ground, influencing the growth of trees and the types of plants that could grow in its environment. Moving into the Cretaceous, we encounter one of the more peculiar and lesser-known dinosaurs, Therizinosaurus. This strange herbivorous theropod had unusually long claws, some of the longest of any known dinosaur, reaching up to 3 feet, 1 meter, in length. With its long claws, large body, and slow, lumbering movement, Therizinosaurus might have looked more like a giant sloth than a typical theropod, but its herbivorous diet and claw morphology suggest it was far from ordinary. Therizinosaurus lived in Asia, around 70 million years ago, and its long claws were likely used to strip leaves from trees, rather than for hunting prey. While the size of its claws suggests it might have been a formidable opponent, most paleontologists believe it was a gentle giant, feeding on vegetation rather than meat. Fossils of this dinosaur are relatively rare, and its bizarre appearance, combined with its herbivorous diet, makes it one of the more fascinating, lesser-known members of the theropod family. Another lesser-known dinosaur from the Cretaceous is Microraptor, a small, feathered dinosaur that lived about 120 million years ago in what is now China. Unlike the massive theropods and sauropods that dominated the Cretaceous landscape, Microraptor was tiny, measuring only about 2.5 feet, 0.75 meters, in length and weighing less than a pound. What makes Microraptor particularly remarkable is its 4 wings. It had feathers on both its arms and legs, allowing it to glide through the air in a manner that predates modern birds. Fossil evidence suggests that Microraptor was an arboreal predator, meaning it lived in trees and likely hunted small vertebrates, such as insects or even small mammals, using its agile flying abilities. Its unique flight adaptation makes it one of the earliest known examples of avian flight, linking dinosaurs to modern birds in an exciting way. However, because of its small size and the fact that it lived in the shadow of larger, more famous dinosaurs, Microraptor is often overlooked in favor of its larger cousins. Finally, let's talk about Amargasaurus, a sauropod from the early Cretaceous period, known for its distinctive spines that ran along its neck and back. Unlike other sauropods, Amargasaurus had two parallel rows of tall, bony spines, which some paleontologists believe could have supported a sail or a series of fleshy structures. These spines likely had some form of thermoregulatory function, helping the animal regulate its body temperature or perhaps serving as a display structure for mating rituals or intimidating rivals. Amargasaurus was not particularly large by sauropod standards, reaching only 33 feet, 10 meters, in length, but its strange appearance and unique adaptations make it a fascinating, lesser-known dinosaur from the Cretaceous. While these dinosaurs are lesser known in popular culture, they each tell an important story about the diversity of life during the Mesozoic era. From the early predators of the Triassic, like Herrerasaurus, to the bizarre, herbivorous giants like Therizinosaurus, these creatures help illustrate the incredible variety of adaptations and niches that dinosaurs occupied. Every fossil discovery brings new insight into this ancient world, allowing us to continue piecing together the incredible tapestry of life that once flourished on Earth. The title of the smallest dinosaur ever discovered belongs to a fascinating little creature called Compsognathus, a tiny theropod that lived during the late Jurassic period, approximately 150 million years ago. Despite its small size, this dinosaur was a highly efficient predator, exhibiting characteristics that allowed it to thrive in its environment. While there have been several contenders for the title of smallest dinosaur, Compsognathus is often regarded as one of the most iconic examples of smallness in the dinosaur kingdom, both for its size and its significant role in the larger narrative of dinosaur evolution. Compsognathus was about the size of a chicken, measuring only 3 feet in length from head to tail and weighing in at just 2.2 pounds. Its body was slim and lightweight, built for speed and agility. With its long slender legs and bipedal posture, Compsognathus was an adept runner, likely chasing down small prey or insects with remarkable swiftness. Its bones were hollow, further reducing its weight and aiding its ability to move quickly through its environment. This dinosaur had a long, thin tail, which would have helped it maintain balance as it ran at high speeds, much like modern-day birds and other fast runners. Its small size also allowed it to navigate through dense underbrush and forested environments, evading larger predators while hunting for smaller creatures. Compsognathus's sharp teeth and clawed fingers suggest that it was a carnivore, preying on small vertebrates, insects, and perhaps even other small dinosaurs. Fossils indicate that its long legs and powerful muscles made it a nimble predator capable of making sudden sharp turns in pursuit of its prey. One of the most remarkable aspects of Compsognathus is that it exemplifies the evolutionary trends of smaller body sizes in dinosaurs. The dinosaur's small stature might have been an evolutionary advantage, allowing it to occupy a unique ecological niche. It could escape the notice of larger carnivores and, at the same time, hunt smaller animals that lived in the same environment. Its size also meant that it needed to consume less food compared to larger dinosaurs, which made survival in times of food scarcity more manageable. Despite its small size, Compsognathus was not a defenseless creature. It had a sharp bite, which would have been useful in both hunting and defense. It likely relied on its agility, speed, and quick reflexes to outmaneuver larger predators. Fossil evidence suggests that Compsognathus lived in areas that had rich vegetation and diverse ecosystems, providing a variety of food sources, from insects to small vertebrates. This flexible diet might have helped it survive in a world full of much larger and dominant predators. While Compsognathus is widely regarded as one of the smallest dinosaurs, Microraptor, a much smaller dinosaur, also competes for the title of smallest dinosaur ever discovered. Microraptor was a feathered theropod that lived during the early Cretaceous, around 120 million years ago. This little dinosaur was even smaller than Compsognathus, measuring only about 2.5 feet in length and weighing less than 2 pounds. Microraptor had an incredibly unique and specialized body with feathers not only on its forelimbs but also on its hind limbs, giving it 4 wings, a characteristic that distinguishes it from most other dinosaurs. These feathered limbs likely allowed Microraptor to glide from tree to tree in much the same way that modern-day birds do. It likely lived in the trees, hunting small vertebrates, birds and insects, using its flight ability to quickly capture prey or evade predators. Microraptor's size made it well suited to life in the forest canopy, where larger animals could not easily access. Its small size and unique features make Microraptor an important figure in the study of dinosaur evolution, particularly in the transition from non-avian dinosaurs to the early ancestors of birds. Its well-preserved fossils have provided critical insight into the development of feathers and the role of flight in the evolution of dinosaurs, challenging the traditional view of dinosaurs being purely terrestrial and helping to bridge the gap between dinosaurs and modern birds. Another contender for the smallest dinosaur is Parvicursor, a diminutive dinosaur that lived during the Cretaceous period. Measuring only about 1 foot in length and weighing less than half a pound, Parvicursor is considered one of the most minuscule dinosaurs in terms of both size and weight. Parvicursor's size and features suggest it was likely an insectivore with a diet consisting of small insects and other tiny invertebrates. Its size would have made it highly vulnerable to larger predators, but its small footprint likely allowed it to dart into tiny crevices or quickly seek cover in its environment. Despite their relatively modest size, dinosaurs like Compsognathus, Microraptor, and Parvicursor were not insignificant players in their ecosystems. They played critical roles in shaping the biodiversity of their environments and helped establish some of the ecological patterns we see in modern ecosystems today. The small size of these creatures allowed them to fill specific ecological niches, such as being fast runners, agile flyers, or insectivores, contributing to the overall balance of the prehistoric world. In addition to their ecological roles, these tiny dinosaurs also demonstrate the incredible diversity in dinosaur evolution. The existence of such small-bodied dinosaurs highlights the fact that dinosaurs, much like modern animals, came in all shapes and sizes. The successful adaptation of small dinosaurs allowed them to thrive in ecosystems teeming with larger predators and herbivores, ultimately influencing the trajectory of dinosaur evolution over millions of years. These small dinosaurs also serve as a reminder of the complexity of life on Earth during the Mesozoic era, where both giant and minute creatures coexisted in dynamic ecosystems. While much attention is often given to the larger, more imposing dinosaurs, is the smaller, often overlooked dinosaurs that help to complete the picture of life in the age of the dinosaurs, revealing the diverse strategies for survival that shaped the world of prehistoric life. From agile runners to flyers, the smallest dinosaurs had a significant impact on the world they inhabited, and they continue to inspire paleontologists and dinosaur enthusiasts alike. One of the most fascinating aspects of dinosaur life is their social behavior, particularly how some species formed herds or engaged in pack behavior for survival. Many dinosaurs, especially herbivores, likely traveled in groups for protection, social interaction, and cooperation. The idea of herding or pack behavior is significant because it sheds light on how these creatures interacted with each other and navigated their environments. By examining fossil evidence and modern analogues, paleontologists have hypothesized about the social structures of different species, such as Triceratops, Parasaurolophus, and Edmontosaurus, which relied on group dynamics for survival. One of the most well-known examples of herd behavior in dinosaurs is Triceratops, a large herbivorous ceratopsid from the late Cretaceous period. The presence of multiple Triceratops skeletons found together in herding sites suggests that these dinosaurs lived in groups, especially during migration seasons or in areas with abundant food. Fossil evidence from sites like the Badlands of Montana shows large numbers of these herbivores gathered together, likely for protection against predators like Tyrannosaurus rex. The social structure of a Triceratops herd was essential for survival. The large frill, combined with sharp horns, made it difficult for predators to attack the herd. When a predator like T-Rex approached, the herd could have used group coordination to fend off the threat. By standing together and using their horns in defense, Triceratops could protect weaker members, creating a united front. This type of group defense is seen in modern herbivores like elephants or bison, where the young are safeguarded within the herd while adults form a protective perimeter. In addition to protection, herding behavior would have allowed for easier migration in search of food. Large herbivores like Triceratops needed significant amounts of plant material to sustain their massive bodies, so traveling in groups to new feeding grounds was efficient. By sticking together, these dinosaurs could also assist each other in navigating through dangerous areas and benefit from the shared knowledge of the group. Social bonds could have been formed through communication, ensuring every member stayed close and worked together to find resources. Another herbivorous dinosaur known for potential herd behavior was Parasaurolophus, a hadrosaur from the late Cretaceous period. Known for its distinctive, backward-curving cranial crest, Parasaurolophus was bipedal and likely lived in large herds. The shape of its crest might have played a role in communication within those herds. Some paleontologists suggest the crest, which could have been hollow, was used for vocalization, emitting sounds that traveled long distances to communicate between individuals in the herd. The social behavior of Parasaurolophus would have been beneficial for both finding food and protecting the herd. Hadrosaur herds were likely large, and in times of danger, the size of the herd could have been a deterrent to predators. Large herds are harder to target, and in a group, members could act as sentries while others fed. Furthermore, members could provide alert signals to warn of approaching threats. Evidence from fossilized footprints suggests that Parasaurolophus traveled in herds. The footprints, found in sites like the Grand Staircase Escalante National Monument in Utah, show coordinated movement, supporting the idea of social groups. These herding sites indicate that Parasaurolophus followed migratory patterns, much like modern herbivores in search of food and water. The presence of multiple individuals in these tracks shows herd behavior was likely a significant part of their daily lives. In contrast to herbivores like Triceratops and Parasaurolophus, some carnivorous dinosaurs also exhibited pack behavior. The most famous example is Velociraptor, a small, agile predator known for its hunting strategies. Fossil evidence, especially from the Dinosaur Park Formation in Canada and the Gobi Desert in Mongolia, suggests that Velociraptor hunted in packs, cooperating to bring down larger prey or surround individuals to overwhelm them. The idea of pack hunting is based on fossilized evidence of multiple individuals found together, some showing signs of injury consistent with group hunting tactics. For instance, in the Gobi Desert, paleontologists discovered fossils of a group of velociraptors near a Protoceratops, a herbivorous dinosaur. Evidence suggests the velociraptors surrounded their prey, using coordination and agility to bring it down. This would have given them an advantage, especially considering their smaller size. By hunting in packs, Velociraptor could take down prey larger than itself, much like modern wolves or lions. While Velociraptor is the most famous example, other carnivorous dinosaurs like dromaeosaurs and some theropods might have also exhibited pack behavior to enhance hunting efficiency. Social living in predators opens up possibilities for complex social structures, such as sharing food or even raising offspring together, though evidence for these behaviors is limited. The study of herd and pack behavior has revolutionized our understanding of dinosaur social dynamics, showing that many species were far more complex than previously thought. Cooperative behaviors, whether for defense, hunting, or migration, highlight the adaptive advantages of living in social groups. These behaviors were essential for survival and for shaping ecosystems, as dinosaurs interacted with each other in a variety of ways. By observing modern animal behaviors and applying them to the fossil record, paleontologists continue to uncover how these ancient creatures lived and thrived. Parenting and nesting behaviors in dinosaurs offer fascinating insights into how these ancient creatures cared for their young. Over the years, paleontologists have uncovered evidence of parental care, nesting sites, and social structures, shedding light on how dinosaurs reproduced and raised their offspring in their environments. Much of what we know about dinosaur parenting comes from fossilized evidence and modern analogues like birds, their closest living relatives. Dinosaurs exhibited various forms of cooperative parenting that would have been essential for the survival of their young in the harsh prehistoric world. One of the most important discoveries was the Maiasaura nesting site. Found in the late Cretaceous period in North America, it contained both eggs and young dinosaurs. Fossilized evidence shows that Maiasaura built nests and returned to care for their young. This suggests that these dinosaurs engaged in active parental care, similar to modern birds. Evidence of these nests being arranged in colony-like structures suggests social behavior, where multiple individuals cooperated to protect their offspring. In addition to Maiasaura, other dinosaurs such as Oviraptor exhibited interesting parental behaviors. Fossils of Oviraptor, once thought to be egg thieves, revealed that these dinosaurs were actually protecting their eggs. Fossils of Oviraptor crouching over nests in a protective manner suggest they incubated eggs, much like modern-day birds that sit on their eggs to keep them warm. Fossil evidence shows that some dinosaurs, such as Protoceratops, may have lived in family groups. Fossilized remains indicate that young Protoceratops were often found alongside adults, which suggests post-hatching care. Parents likely stayed close to their young, protecting them until they were capable of surviving independently. Carnivorous dinosaurs, including Tyrannosaurus rex and Velociraptor, may have also practiced parental care. Evidence suggests that these predators might have cared for their young for extended periods. Fossilized nests and bone beds show that T. rex raised their young near adults, offering them protection. This level of care might have been essential for young T. rex, who likely depended on their parents for survival in their early life stages before they could hunt on their own. In some species, like Velociraptor, there may have been cooperative breeding or group parenting strategies. Fossilized evidence from sites containing multiple young and adult dinosaurs hints at the possibility that Velociraptor or similar species may have engaged in group care. This could have provided added protection and nurturing during the early stages of life. Dinosaurs also exhibited a wide range of nesting behaviors. Some species, like Maiasaura, built complex nests, while others, like sauropods, laid their eggs in simple clusters. Some dinosaurs may have even laid their eggs in hidden areas or created mound nests for protection. This variety of nesting strategies highlights the adaptability of dinosaurs to different environments. Troodon, a small theropod, may have even nested in trees, with evidence suggesting they created platform nests. These tree nests would have offered protection from predators, similar to modern-day tree-nesting birds. The adaptability of these nesting strategies allowed dinosaurs to raise their young in diverse habitats. Overall, the discovery of parenting and nesting behaviors in dinosaurs has reshaped how we understand their biology. Dinosaurs were not simply cold-blooded creatures leaving their young to fend for themselves. Many species, including Maiasaura, Oviraptor, and Tyrannosaurus rex, exhibited complex parental care, often in cooperative and social structures. These behaviors ensured the survival of their offspring, contributing to the continuation of their species. As paleontologists continue to discover more fossil evidence, we gain a deeper understanding of the nurturing side of dinosaurs and how they interacted with their environment and each other. Mating rituals and displays in dinosaurs offer a fascinating look into their social structures and reproductive behaviors. Though direct evidence is scarce, paleontologists have used fossilized remains, footprints, and comparisons with modern animals, particularly birds and reptiles, to infer how dinosaurs might have courted mates, competed for dominance, and engaged in social interactions. Like many modern animals, dinosaurs likely employed visual displays, vocalizations, and physical behaviors during mating rituals to attract mates, establish territory, and assert dominance. Much like today's peacocks or birds of paradise, where males show off their feathers or movements to impress females, dinosaurs may have used horns, crests, or frills for similar purposes. A famous example is the Triceratops, a herbivorous dinosaur with a large frilled neck and 3 horns. These features might have played a role in mating displays. The size and shape of the frill could have indicated health or strength, traits often associated with reproductive success in animals. Males with more impressive frills might have had an advantage in attracting females. Triceratops males could have shown off their physical strength, positioning themselves in front of females and flaunting their horns and frills. Similarly, the Parasaurolophus, a type of hadrosaur, had a long, curved crest extending from its head. The size and shape of the crest varied, and larger ones may have signaled better genetics or physical prowess. Males likely displayed their crests during courtship, using their size and shape to impress potential mates. Additionally, these crests might have functioned as resonating chambers, creating vocalizations to communicate with rivals or attract mates. Theropods like Velociraptor and Oviraptor also likely engaged in mating displays, especially because many were feathered. Modern-day birds use their feathers to attract mates, and feathered dinosaurs might have done the same. Feathers could have been ruffled or displayed in intricate patterns to show off the male's fitness. Fossils show evidence of feather structures in theropods, and males might have used these to create visually appealing patterns, much like the tail feathers of peacocks. Vocalizations were likely important too. Many theropods, especially species like Tyrannosaurus rex, probably communicated through calls or roars. These vocalizations could have been used to assert dominance, warn rivals, or attract mates. For example, a T-Rex might have used a deep, rumbling call to announce its presence or ward off competitors, signaling to others during mating seasons. Additionally, ceratopsians like Styracosaurus and Chasmosaurus had large frills and spikes, which may have been used for mating displays. Males with larger or more colorful frills may have been more successful in attracting mates. Such features likely also played a role in combat with rival males, demonstrating the male's physical strength and dominance. In some species, like Maiasaura, males may have showcased their nesting sites as a form of courtship. Fossils suggest that these dinosaurs lived in colonies, and males likely displayed their nests to signal their ability to care for offspring. Successful males may have created prime nests, showcasing their strength and ability to provide, similar to modern animals like albatrosses, where males establish territories to win the favor of females. In many species, physical competition among males was crucial. Fossil evidence of battle wounds shows that males fought to establish dominance and secure mating rights. In ceratopsians, large horns were likely used in such contests. These horns were not only for defense but also for direct combat between males. The victorious male might then earn the right to mate with the female. Mating seasons in dinosaurs might have been influenced by environmental factors, such as food availability or seasonal changes. Similar to how animals today synchronize reproduction with abundant resources, herbivorous dinosaurs might have timed their mating and nesting to coincide with periods of plentiful vegetation, ensuring that their young would have access to sufficient food during early development. While much of this is speculative, the fossil record offers valuable clues about dinosaur mating behaviors. From visual displays to vocalizations and physical combat, dinosaurs likely had complex courtship rituals to attract mates, establish dominance, and ensure reproductive success. As new fossils are discovered, we may uncover even more details about these ancient rituals, helping us better understand the social lives of these incredible creatures. Diet and feeding habits in dinosaurs were as diverse as the species themselves. Dinosaurs, like modern animals, adapted to various ecosystems and developed specialized diets that allowed them to thrive during the Mesozoic era. From towering sauropods feeding on the tallest trees to terrifying theropods that hunted prey with razor-sharp teeth, dinosaurs developed unique feeding strategies suited to their needs. At the most basic level, they can be divided into three primary dietary categories: herbivores, carnivores, and omnivores. Each category came with its own set of adaptations which significantly influenced how dinosaurs interacted with their environment. Herbivores were the plant eaters of the dinosaur world, and they came in many shapes and sizes. The sauropoda group, including dinosaurs like Brachiosaurus and Apatosaurus, were among the largest herbivores. These enormous creatures fed on ferns, conifers, and other plants. Their long necks allowed them to reach the tallest trees, giving them access to a food source other animals couldn't reach. This adaptation, combined with their massive size, allowed them to gather vast quantities of plants with minimal effort. Interestingly, sauropods spent much of their day feeding in herds. This strategy may have offered protection from predators and allowed them to access vast amounts of vegetation over larger areas. The Apatosaurus, for instance, roamed in large herds, using its teeth to strip leaves off branches. Their teeth, resembling flat spatulas, were perfect for cropping and processing soft, fibrous vegetation. In contrast, smaller herbivores like Hypsilophodon or Iguanodon may have had a more varied diet, including bushes and shrubs. These dinosaurs were typically bipedal and much smaller than sauropods, so their feeding habits focused more on grazing on lower-growing plants. Their teeth were suited to chewing, with structures that could break down plant material for digestion. Additionally, some species like Iguanodon had large thumb spikes, which could have been used for defense or uprooting plants. Some herbivores had specialized adaptations. The Stegosaurus, for example, had a small head compared to its massive body. Its teeth were simple and peg-like, suggesting it fed on softer vegetation like ferns and cycads. Its plates and spikes likely served as defense but may have also helped with communication or temperature regulation. On the other end of the spectrum were carnivores, dinosaurs that hunted other animals. Among these predators, the theropoda group stands out, including famous dinosaurs like Tyrannosaurus rex and Velociraptor. These predators had sharp teeth and claws, perfect for gripping and tearing meat. They were fast, agile, and had keen senses to help them stalk and capture prey. The Tyrannosaurus rex was one of the largest land predators to ever live. It had massive, serrated teeth capable of crushing bone, indicating it wasn't just a scavenger but a skilled predator. The T-Rex likely used its powerful jaws to hunt large herbivores like Triceratops and Edmontosaurus. Its keen sense of smell may have helped it detect prey from miles away, and its muscular legs allowed it to chase and overpower slower prey. Other carnivores like the Velociraptor likely hunted in packs. The Velociraptor had sharp claws and teeth but wasn't as large as T-Rex. Instead, it relied on speed and coordination with other pack members to bring down larger prey. Evidence suggests the Velociraptor may have had feathers, which would have helped with thermoregulation and communication during hunts. Like modern predators, the Velociraptor used agility and sharp senses to target weak or vulnerable prey. The Allosaurus, another well-known carnivore from the late Jurassic period, was one of the largest predators of its time. It had large, curved teeth for slicing flesh, and its powerful jaws allowed it to tear through its prey. Unlike T-Rex, which had relatively small arms, the Allosaurus had relatively long arms, which may have helped it grasp and subdue prey. It likely targeted smaller herbivores but could have also taken down larger animals through teamwork and strength. There were also omnivorous dinosaurs that ate both plants and animals. The oviraptor is a classic example. Although initially thought to be a strict carnivore due to its toothless beak, evidence suggests it may have fed on a varied diet of small animals, plants, and even eggs. The Archaeopteryx, considered one of the first birds, likely had a similar diet, eating insects, fruits, seeds, and small vertebrates. In addition to specialized teeth, jaw structures, and claws, many dinosaurs had digestive systems adapted to their diets. Herbivorous dinosaurs, for instance, often had complex stomachs to help break down tough plant material. Some sauropods like the Brachiosaurus may have had a ruminant-like system, where food was processed in multiple stages to extract as many nutrients as possible from plant matter. Carnivores, on the other hand, likely had shorter, more straightforward digestive systems suited for breaking down protein-rich food. Their stomach acids would have been highly concentrated to break down tough tissues in animal prey. Fossil evidence shows that carnivorous dinosaurs often had large ribcages and strong jaws capable of handling large meals. Some, like the Spinosaurus, were even semi-aquatic and capable of hunting both on land and in water. One of the most fascinating aspects of dinosaur feeding habits is their relationship with ecosystems. Dinosaurs were a crucial part of the ancient food chain, and their interactions with plants and other animals shaped the environments they lived in. Herbivores like Stegosaurus and Triceratops were primary food sources for large carnivores like T-Rex, while smaller herbivores fed on shrubs and low-lying vegetation, helping to shape plant life. In conclusion, dinosaur diets were as varied as the species themselves. From towering herbivores to razor-sharp carnivores and opportunistic omnivores, each dinosaur evolved to take advantage of the resources in their environment. By studying their teeth, jaws, and feeding behaviors, paleontologists have uncovered a wealth of information about how these magnificent creatures lived and interacted with their ecosystems. As new fossils continue to be discovered, our understanding of dinosaur diets will only deepen, shedding more light on the diversity of life during the Mesozoic era. Migration and herding behaviors in dinosaurs have long fascinated paleontologists and researchers as they provide insight into the complex social and environmental interactions of these ancient creatures. Like modern animals, many dinosaurs adapted to their surroundings in such a way that they could move across vast distances, often following food sources or seeking better climates. The evidence of migration and herding behaviors found in fossils suggests that these behaviors were not only widespread but played a crucial role in the survival of various species. The concept of migration in dinosaurs is intriguing, as it demonstrates that these animals were capable of long-distance travel. The fossil record indicates that some species of dinosaurs moved seasonally, likely driven by changes in climate, food availability, and the need to find safe breeding grounds. For example, the large herbivores of the Mesozoic era might have migrated to find food sources during different seasons. This migration could have been similar to the migratory patterns observed in modern-day herbivores, like wildebeest or caribou, which travel in search of better grazing grounds. In addition to food, climate played a significant role in driving dinosaur migration. Evidence suggests that some may have migrated to avoid extreme conditions, particularly during seasonal temperature fluctuations. Some regions that were once home to dinosaurs may have experienced drastic changes in climate, leading to the need for dinosaurs to travel to areas where conditions were more favorable for survival. For instance, during the colder months, some species might have moved to warmer regions to avoid freezing temperatures, similar to the migration patterns of modern-day animals. Herding behavior, particularly in herbivorous dinosaurs, was another key adaptation that helped ensure survival. Herds provided protection from predators, a key factor for species that were large and slow-moving. For example, the Brachiosaurus and Apatosaurus were likely part of large herds that roamed the land in search of food. These herds, which could number in the hundreds or even thousands, would have provided safety in numbers, as predators would have been less likely to single out a single individual from such a large group. Herding also allowed for more efficient foraging, as the group could move from one feeding area to another in a coordinated manner. The evidence for herding behavior in dinosaurs comes from several sources, including fossilized trackways and bone beds. Fossilized footprints from groups of dinosaurs indicate that they often move together, with individuals walking in the same direction at the same time. In some cases, fossilized remains of herds have been found in bone beds, which are areas where a large number of animals died and were buried together. These bone beds provide further evidence that these dinosaurs lived in groups, possibly for protection or social interaction. Some herbivorous dinosaurs, like the hadrosaurs, duck-billed dinosaurs, likely traveled in large herds during migration. These herbivores were known for their complex social structures and their ability to adapt to a variety of environments. Hadrosaurs had a wide geographical range, and fossil evidence suggests they moved between regions in search of food and breeding grounds. Their herding behavior would have provided safety from carnivores, which were common threats in the Mesozoic era. Carnivorous dinosaurs also exhibited some forms of herding behavior, although it was typically less pronounced than in herbivores. The Velociraptor, for example, is believed to have hunted in packs, similar to modern-day wolves. This cooperative hunting strategy allowed them to bring down prey that was much larger than themselves. Fossil evidence suggests that some theropods, including the Velociraptor and Deinonychus, may have traveled together in groups, possibly for both hunting and social reasons. Their pack behavior would have provided them with an advantage in hunting and would have allowed them to work together to outsmart their prey. In contrast to the relatively cooperative nature of some carnivorous dinosaurs, other predators, such as the Tyrannosaurus rex, likely exhibited more solitary behavior. The T-Rex, one of the largest and most fearsome predators of its time, was likely a solitary hunter that did not rely on pack dynamics to catch prey. Evidence from fossilized bite marks and the wear patterns on T-Rex teeth suggests that it used its powerful jaws to tear through its prey, likely focusing on large herbivores like Triceratops. However, some paleontologists speculate that T-Rex may have engaged in social behaviors, such as hunting in pairs or defending territories together, based on evidence of interactions between individuals of the same species found in fossilized remains. The fossilized remains of young dinosaurs also provide insight into the social behaviors of herding species. For many species, such as sauropods, it is believed that the younger individuals traveled alongside adults in herds for protection and guidance. In some cases, fossilized skeletons of juvenile dinosaurs have been found together in locations that suggest they traveled together before they reached adulthood. This cooperative behavior among generations likely helped ensure the survival of the species, as the young would have benefited from the protection and knowledge of the older individuals. The presence of migration and herding behaviors in dinosaurs highlights the complexity of their social structures. These behaviors were essential for survival in the harsh environments of the Mesozoic era, allowing species to find food, avoid predators, and reproduce successfully. By studying these behaviors through fossil evidence, paleontologists have gained a better understanding of how dinosaurs lived and interacted with each other. Migration and herding behaviors were fundamental to the survival of many dinosaur species. These behaviors allowed dinosaurs to adapt to changing climates, find food, and protect themselves from predators. The fossil evidence of these behaviors continues to shed light on the social lives of dinosaurs, offering a glimpse into the complex and dynamic ecosystems in which they thrived. As new discoveries are made, our understanding of dinosaur migration and herding will only continue to evolve, revealing even more about the lives of these ancient creatures. Dinosaur intelligence is one of the most captivating puzzles in paleontology, a window into how creatures from a bygone era might have thought, learned, and interacted with their world. When picturing dinosaurs, many imagine massive, lumbering reptiles driven solely by instinct. Yet fossil evidence and modern comparisons suggest that some dinosaurs possessed surprising cognitive abilities that extend far beyond basic survival. A key factor used to assess dinosaur intelligence is the encephalization quotient, EQ, which compares brain size to body mass. Although many dinosaurs had relatively small brains compared to their enormous bodies, some theropods, such as Velociraptor and Tyrannosaurus rex, had higher EQs. A higher EQ implies more complex brain structures and the potential for advanced behaviors like problem-solving, strategic hunting, and social interaction. For example, Velociraptor is often portrayed as an exceptionally cunning predator. Despite its small size, its brain-to-body ratio suggests it possessed rapid decision-making skills. Fossil evidence hints that velociraptors may have hunted in packs, coordinating their movements to corner prey much like modern wolves. Such teamwork would have required not only physical agility but also a degree of social intelligence and communication, implying that these agile dinosaurs could plan and execute complex hunting strategies. Tyrannosaurus rex, frequently depicted as the quintessential dinosaur brain, also shows signs of advanced cognition. Although its brain was modest relative to its gigantic skull, T. rex possessed extraordinarily large olfactory bulbs. This keen sense of smell likely enabled it to track prey over long distances, plan ambushes, and even scavenge intelligently. Its ability to integrate visual and olfactory cues suggests that T. rex could process environmental information effectively and adapt its hunting strategy accordingly. Not all dinosaurs with smaller brains were dumb. Many herbivorous dinosaurs, such as the hadrosaurs, duck-billed dinosaurs, lived in large, coordinated herds and likely developed social intelligence focused on group communication and survival. Fossilized trackways and bone beds indicate that hadrosaurs often moved in organized groups, possibly using vocalizations, body language, or subtle color changes to communicate. Such social behaviors imply a level of cognitive sophistication geared toward group survival, even if it was not as complex as modern primate interaction. The transitional dinosaur Archaeopteryx also offers intriguing clues. Often considered one of the first birds, Archaeopteryx had a relatively large brain for its body size and well-developed regions for vision and coordination. This anatomy suggests it could perform intricate flight maneuvers and exhibited advanced motor control and spatial awareness. Its brain structure, bridging reptilian and avian traits, hints at the emergence of complex behaviors that would later define modern bird intelligence. In contrast, many enormous sauropods, like Brachiosaurus, had brains that were small relative to their massive bodies. These giants, which could reach lengths of up to 80 feet, relied on basic instincts for functions such as feeding and locomotion. Their simpler neural architecture may have been sufficient for routine tasks in predictable environments, reflecting a more instinctual mode of behavior. Another important aspect of dinosaur intelligence involves sensory capabilities. For instance, T. rex's enormous olfactory bulbs and large, binocular eyes were not only vital for hunting but also for navigation and territorial behavior. Similarly, the presence of feathers on some theropods, such as Velociraptor, suggests they possessed a refined sense of touch, which would have been crucial for exploring their environment and communicating subtle cues. These well-developed sensory systems likely provided dinosaurs with critical information for rapid decision-making. The relationship between brain structure and behavior offers further insights. Certain dinosaurs likely had specialized brain regions dedicated to particular tasks. The Stegosaurus, with its famously small brain relative to its body size, probably relied on instinctual behaviors for feeding and defense. Its limited cognitive capacity meant that its actions were largely reflexive, focused on foraging and using its tail spikes for protection, while more complex behaviors were unnecessary for survival. In contrast, dinosaurs such as Trudon, often cited as one of the smartest, had relatively large brains compared to their body size. Trudon, a small, bird-like theropod from the late Cretaceous, possessed anatomical features that suggest advanced sensory integration and problem-solving abilities. Believed to be omnivorous, Trudon likely foraged intelligently for both small animals and plant matter. Its brain structure indicates a high capacity for learning and adaptability, traits that would have been particularly useful in a rapidly changing environment. The cognitive abilities of dinosaurs can also be inferred from their reproductive behaviors. Fossilized nesting sites, such as those of Maiasaura, indicate that some species engaged in extended parental care. Constructing nests, protecting eggs, and nurturing hatchlings require planning, coordination, and learning, all behaviors associated with higher intelligence. Such parental investment not only improved offspring survival but also suggests a level of social complexity that goes beyond simple instinct. The study of dinosaur intelligence continues to evolve as new fossils and advanced imaging techniques provide fresh insights. Each discovery refines our understanding of how these ancient creatures used their senses, solved problems, and interacted within their social groups. Whether it was the tactical coordination of pack hunters or the subtle social interactions of herd dwellers, dinosaur brains reveal a complex spectrum of cognitive abilities. This diversity challenges the outdated notion of dinosaurs as merely instinct-driven giants, instead highlighting them as dynamic beings capable of intricate thought and behavior. Overall, the study of dinosaur intelligence continues to evolve as new discoveries reshape our view of dinosaur cognition and their behavioral repertoire. Dinosaur evolution is one of the most captivating stories in the history of life on Earth. Today we travel back to a time when the world was young and the planet transformed after a catastrophic mass extinction. In that ancient landscape, a new group of reptiles emerged that would come to dominate the Earth for millions of years. The evolution of dinosaurs is a tale of survival, adaptation, and remarkable diversity. It all began in the early Triassic period, when Earth was recovering from a mass extinction that wiped out most previous life. In that harsh environment, small and agile reptiles developed traits that set them apart. They evolved an upright stance with legs positioned directly beneath their bodies, a change that allowed for more efficient movement and laid the groundwork for a dramatic increase in size. This posture gave these early dinosaurs a major evolutionary advantage that paved the way for the incredible forms to come. As the Triassic gave way to the Jurassic, dinosaurs began to diversify and fill every available niche. Some evolved into swift, predatory hunters while others grew into enormous plant eaters. Two major groups emerged based on differences in hip structure. One group later became known as the lizard-hip dinosaurs, which included the ancestors of both colossal sauropods and fierce theropods. The other group, the bird-hip dinosaurs, evolved into a range of herbivorous forms that thrived in many environments. During the Jurassic period, the Earth experienced a burst of dinosaur diversity. Enormous sauropods such as Brachiosaurus and Apatosaurus roamed the land with long necks reaching high into treetops to feed on vegetation. These giants moved slowly but steadily across vast landscapes, their enormous bodies and elongated necks allowing them to gather large quantities of food. At the same time, agile predators like Allosaurus honed their hunting skills using speed, sharp claws, and powerful jaws to capture prey. In this dynamic ecosystem, predators and herbivores coexisted in an intricate food chain. When the Jurassic transitioned into the Cretaceous, dinosaur evolution reached a peak of specialization and diversity. The world became a mosaic of different environments, from lush forests and rolling plains to arid deserts and coastal regions. Herbivorous dinosaurs became even more specialized, with some evolving intricate dental structures to process tough plant material, while others, such as the duck-billed hadrosaurs, developed complex social behaviors. These hadrosaurs likely moved in large herds and communicated with one another to avoid predators and maintain social bonds. Carnivorous dinosaurs also continued to evolve during the Cretaceous. Tyrannosaurus rex emerged as one of the most fearsome predators ever to walk the earth. With a massive skull, powerful bite, and keen sensory abilities, T-Rex dominated its territory by preying on large herbivores and scavenging when opportunities arose. Meanwhile, smaller predators like Velociraptor evolved remarkable agility and may have hunted cooperatively, displaying a level of social coordination that allowed them to take down prey larger than themselves. One of the most dramatic developments during the Cretaceous was the emergence of feathered dinosaurs. Fossils have revealed that many theropods sported feathers, a trait that likely began as insulation or display and later paved the way for the evolution of flight. This discovery has reshaped our understanding of dinosaur evolution and established the link between non-avian dinosaurs and modern birds. The evolution of flight allowed these creatures to explore new ecological niches and gave rise to early birds, whose descendants populate our skies today. Despite their incredible diversity and success, the reign of the dinosaurs came to an abrupt end 66 million years ago when a massive asteroid impact and extensive volcanic activity triggered global environmental changes. The resulting drop in temperature and collapse of food chains led to the extinction of most dinosaur species. Yet one branch of their evolutionary tree survived, the small, feathered dinosaurs that eventually evolved into birds, preserving the legacy of dinosaurs in a form that continues to thrive. New fossil discoveries and advances in technology have revolutionized our understanding of dinosaur evolution. Scientists now use advanced imaging and computer modeling to reconstruct dinosaur anatomy and simulate how these magnificent creatures moved, fed, and interacted with their environment. Every new discovery adds another piece to the puzzle, revealing an evolutionary history that is as dynamic and complex as life itself. In conclusion, the evolution of dinosaurs is a story of innovation, adaptation, and survival. From their humble beginnings in a post-extinction world to their rise as the dominant land animals and eventual transformation into birds, dinosaurs occupied nearly every ecological niche and left an indelible mark on the history of life. Their journey from small, agile reptiles to gigantic, specialized creatures stands as a testament to the power of evolution. Although their reign ended abruptly, the legacy of dinosaurs lives on in the birds that fly overhead and in the continued discoveries that reshape our understanding of life on Earth. Dinosaur extinctions rank among the most dramatic events in Earth's history, marking a turning point that reshaped life on our planet. In this first part of our exploration of extinction theories, we delve into one of the most widely discussed hypotheses, the asteroid impact theory. This theory holds that a colossal extraterrestrial collision played a pivotal role in the mass extinction event that ended the reign of the dinosaurs, setting off a cascade of environmental disasters that wiped out countless species. The impact hypothesis gained widespread attention when scientists discovered an anomalously high concentration of a rare metal in sedimentary layers from the end of the Cretaceous period. This metal, abundant in asteroids but scarce on Earth, provided an early clue that a massive impact had occurred. Researchers soon linked this finding with the discovery of a giant crater buried beneath the Yucatan Peninsula, a structure so immense that it suggested the collision released energy comparable to billions of nuclear bombs exploding at once. The sheer scale of this impact would have produced immediate and catastrophic consequences. The collision would have vaporized rock at the impact site, sending shock waves rippling through the Earth's crust. Debris and dust were hurled high into the atmosphere, forming a global cloud that blocked sunlight for an extended period. With sunlight obscured, photosynthesis came to a standstill, plunging the planet into a prolonged period of darkness and cold. Without light, plant life would have withered, setting off a chain reaction that starved herbivores, which in turn left carnivores without prey. Wildfires likely ignited almost instantaneously. The tremendous heat generated by the impact could have sparked fires over vast areas, further devastating ecosystems already stressed by the sudden loss of sunlight. The combination of an impact winter and rampant fires would have created an environment inhospitable to most life forms. Even species adapted to harsh conditions would have found survival nearly impossible amid the rapidly changing climate. Despite the compelling evidence supporting an asteroid impact, some scientists have proposed alternative explanations, such as massive volcanic eruptions. The volcanic activity in the Deccan Traps of India, for instance, released enormous amounts of lava and gases over an extended period. These eruptions could have gradually altered the climate by increasing atmospheric carbon dioxide and inducing long-term warming, while also triggering acid rain that would have damaged ecosystems. However, many researchers maintain that the abrupt, global-scale devastation observed in the fossil record is best explained by a sudden impact rather than a series of gradual volcanic events. The discovery of the Chicxulub crater, named after the nearby town in Mexico, has become central to the impact hypothesis. This crater spans over 150 kilometers in diameter, a size that matches the energy output needed to trigger the global extinction event. Geological studies of the crater have revealed shock-metamorphosed minerals and other evidence of high-pressure impacts, lending further support to the notion that a massive asteroid collision was the primary driver behind the mass extinction at the end of the Cretaceous. Computer simulations have also played an important role in refining the impact theory. Models suggest that the collision would have generated megatsunamis and triggered seismic events across the globe. These simulations help us understand how the impact could have led to rapid climate changes, such as sudden cooling from blocked sunlight and subsequent warming as the dust settled. The speed and magnitude of these environmental shifts help explain why so many species, including the non-avian dinosaurs, disappeared so abruptly. The abruptness of the extinction is a critical aspect of the impact theory. In many regions, the fossil record shows a sharp boundary between the thriving ecosystems of the late Cretaceous and the barren landscapes that followed. This sudden disappearance of species aligns with a catastrophic event rather than a slow, gradual decline. While volcanic activity and other environmental factors may have contributed to a stressed ecosystem, the evidence points to a singular, overwhelming event as the final blow. Even as scientists debate the relative roles of asteroid impact and volcanic activity, one thing remains clear: the end of the Cretaceous marked a profound transformation in Earth's biosphere. The extinction event cleared the way for the rise of mammals and ultimately, the evolution of humans. Although the non-avian dinosaurs were wiped out, their avian descendants survived and continue to populate the planet, carrying the legacy of these ancient creatures into the present day. The study of extinction theories is not merely an academic exercise, it offers vital insights into how life on Earth responds to catastrophic events. Understanding the mechanisms behind the mass extinction of the dinosaurs helps us comprehend the resilience and adaptability of life. It also serves as a reminder that even the most dominant species can be vulnerable to sudden environmental changes. In summary, the asteroid impact theory presents a compelling explanation for one of the most dramatic mass extinctions in history. The discovery of a global layer enriched with rare metals, the identification of the massive Chicxulub crater, and the results of sophisticated computer models all point to a sudden, catastrophic event that altered Earth's climate and ecosystems in an instant. While alternative theories exist, the weight of evidence supports the idea that a colossal asteroid impact set off a chain of environmental disasters that ultimately ended the age of dinosaurs. As we continue our exploration of extinction theories, The next sections will examine other hypotheses and the interplay of various factors that may have contributed to this monumental event. For now, the impact theory remains a cornerstone in our understanding of how a single, extraordinary event can reshape the course of life on Earth. Dinosaur extinctions are among the most dramatic events in Earth's history, marking a turning point that reshaped life on our planet. In this third part, we explore the interplay of extinction factors and the aftermath of that global catastrophe. Rather than a single cause, the end of the Cretaceous appears to have resulted from multiple interacting stresses that together overwhelmed the biosphere. The asteroid impact that created the Chicxulub crater is one of the most widely accepted explanations for the mass extinction. When a colossal asteroid collided with Earth, it released an immense amount of energy, vaporizing rock and ejecting debris into the atmosphere. This debris formed a global cloud that blocked sunlight and triggered an impact winter. With photosynthesis abruptly halted, plant life withered and died, setting off a chain reaction that starved herbivores and, in turn, the predators that depended on them. At the same time, massive volcanic activity in the Deccan Traps was altering the global climate. Enormous volumes of lava poured out repeatedly over hundreds of thousands of years, releasing vast quantities of gases into the atmosphere. The steady outpouring of carbon dioxide enhanced the greenhouse effect, gradually raising global temperatures, while sulfur compounds produced acid rain and acidified the oceans. These sustained changes undermined ecosystems by disrupting weather patterns and altering the chemical balance of soils and water, making it difficult for plants and animals to survive. The interplay of these events created a scenario in which ecosystems were hit from multiple directions. The immediate shock of the asteroid impact caused a rapid collapse of food chains, while the persistent effects of volcanic emissions eroded the resilience of life over time. The sudden disappearance of numerous species, as recorded in the fossil record, suggests that the combined stresses pushed ecosystems past a tipping point, leaving little time for adaptation or recovery. The compounded environmental pressures had far-reaching consequences that extended well beyond the extinction event itself. With the disappearance of dominant groups such as large herbivores and carnivores, ecological niches were suddenly left vacant. This opened the door for survivors to diversify and fill new roles. Mammals, which had lived in the shadows of the dinosaurs, experienced a rapid evolutionary expansion in the wake of the extinction event. In the oceans, acidification and temperature shifts led to the collapse of established marine communities, paving the way for the evolution of new species of fish and invertebrates. The idea that mass extinctions result from a single cause has given way to a more nuanced view, in which multiple factors interact in complex ways. In the case of the Cretaceous-Paleogene extinction, the sudden, catastrophic impact of an asteroid combined with the prolonged stress of volcanic activity to create a perfect storm of environmental change. The asteroid's shock waves and global dust veil initiated an abrupt crisis, while the ongoing volcanic activity steadily degraded the Earth's climate and ecosystems. Together, these factors overwhelmed the adaptive capacities of countless species. Computer models and geochemical analyses lend support to this integrated view. Simulations show that the asteroid impact would have generated megatsunamis, triggered seismic events worldwide, and produced rapid, dramatic cooling followed by gradual warming as the atmosphere cleared. Meanwhile, measurements of volcanic elements in sediment layers revealed that the Deccan Traps eruptions coincided closely with the extinction event, suggesting that volcanic activity was not a minor side effect but a major contributor to the environmental crisis. The timing and scale of these events, taken together, paint a picture of a world pushed to its limits by a series of catastrophic changes. The aftermath of this extinction was profound and far-reaching. As ecosystems collapsed, the surviving species faced an entirely altered world. In many regions, the fossil record shows a sharp boundary between the rich diversity of the late Cretaceous and the barren landscapes that followed. This abrupt transition underscores the severity of the combined extinction forces. With the disappearance of the non-avian dinosaurs, the stage was set for the rise of new life forms. Mammals and early birds, among others, took advantage of the empty ecological niches, eventually giving rise to the diversity of species we see today. The legacy of these extinction events is not merely a tale of loss but also one of renewal and transformation. The dramatic collapse of ecosystems forced surviving species to adapt rapidly, spurring an evolutionary renaissance. This adaptive burst not only redefined the course of life on Earth but also serves as a reminder of the resilience of life in the face of overwhelming change. In summary, the mass extinction at the end of the Cretaceous was not the result of a single cataclysm but emerged from the interplay of multiple forces. The sudden, global shock of an asteroid impact combined with the prolonged, cumulative effects of volcanic eruptions to create a tipping point beyond which ecosystems could not recover. The subsequent collapse of food chains and habitats set the stage for a dramatic evolutionary turnaround that allowed new groups, such as mammals and birds, to flourish. As scientists continue to refine their models and uncover new fossil evidence, our understanding of these interconnected factors deepens, revealing the dynamic and often unpredictable nature of life on Earth. Dinosaur stories have captivated human imagination for generations, weaving together science, mystery, and wonder into a saga that transcends time. In this final part, we reflect on what we have learned about these magnificent creatures and their extraordinary journey through Earth's history. From the first humble dinosaurs emerging in the wake of ancient extinctions to their rise as the dominant land animals for millions of years, these giants adapted to changing climates, shifting continents, and fierce competition. We have explored their evolution, intelligence, feeding habits, migration patterns, and the dramatic factors that led to their extinction. Each chapter of their story reveals not only their incredible diversity but also the resilience and adaptability of life itself. Paleontologists continue to unearth new fossils and use advanced technologies to reconstruct the lives of dinosaurs, piecing together clues from bones, footprints, and even soft tissues preserved over millions of years. With every discovery, our understanding deepens, reminding us that dinosaurs were not merely static relics of the past but dynamic, evolving organisms that once roamed vast landscapes. Their legacy lives on in the birds that soar today, echoing the ancient rhythms of survival, adaptation, and evolution. As we conclude our journey through the age of dinosaurs, we are left with a profound sense of wonder and a renewed appreciation for the complexity of life on Earth. The extinction of non-avian dinosaurs, while marking the end of an era, also paved the way for new forms of life to flourish. The story of the dinosaurs is a testament to the ever-changing tapestry of life, illustrating how environmental upheavals can transform entire ecosystems. In the end, the tale of the dinosaurs is one of both loss and renewal. It challenges us to contemplate the fragility of life and the relentless march of evolution. As we look to the future, their story encourages us to explore our own origins and the forces that continue to shape life on our planet. Though the dinosaurs have long vanished from the Earth, their memory endures, etched in rock, captured in science, and forever a source of inspiration and mystery. Their legacy reminds us that from the ashes of extinction, new life can emerge, and that the story of evolution is one of constant change and endless possibility. This enduring saga inspires us to cherish the natural world and to marvel at the profound forces that shape all life every day.